Hi, my name is Eugene Zhang, and today we are going to present what we accomplished during our project of implementing task-oriented dialogue systems, specifically the Mem2Seq model. Here is our table of contents. In this section, I will explain our problem and the details of the system we replicated. Our topic is task-oriented dialogue systems. It has the purpose of helping the users to achieve specific goals, such as restaurant reservation. Here we brought an example of the usage of this task-oriented dialogue system. The user's utterances are on the left, and the system's responses are on the right. At the end of the conversation, the system generates an API call to complete the given task. As you can see, a user can accomplish a task through conversation with the system. So, given these systems, we define the following problem statement. How can such a system understand the user's intent and messages while effectively incorporating knowledge about the task? We chose this paper on the Mem2Seq system for replication. The Mem2Seq model had the best performance among other models, and the system has an elaborate encoder-decoder structure that we wanted to make improvements to. Also, the system is unique in that it is based on generation, unlike other methods and systems that usually approach the task as a classification task. We used the Bobby dataset for training and testing, just as the original Mem2Seq paper did. Bobby is a simulated dialogue dataset with 1,000 questions each for training and testing. It has 5 end-to-end dialogue learning tasks and has specific domain of restaurant reservations. Also, it breaks down a task-oriented dialogue into several subtasks to verify functional capabilities of this task. First, in issuing API calls, that's task 1. The system is used to make a query that includes the user's request information. For task 2, updating API calls, users ask to update their query. Then the system should issue an updated API call. The task 3 is based on the user's request. The system must propose options and corresponding API calls to users based on the knowledge base until the user accepts one of these options. If the user asks for extra information, that's task 4. The system must provide relevant information from the knowledge base. The combination of all tasks 1 through 4 gives us the full dialogue task of task 5. This is the format in which the dataset is in. Here's an example of a dialogue from task 1. The ID resets to 1 at the beginning of a new dialogue and increments as the dialogue goes on. When the bot speaks twice in a row, the special token silence is used to fill in for the missing user utterance. The goal of the task is to predict the bot utterances, which can be either sentences or API calls. And these are noted by the special token API call. Here are some of the terms that will be seen in the research. The collection of subject, relation, and object is called knowledge. It's the information that the system needs to know how to carry out tasks, and it is incorporated in this form of knowledge. For instance, to incorporate the information that the fancy pub is located in London, it can be expressed in this triple form, as you can see. Memory is a set of trainable embedding matrices that map tokens into embeddings. Here, tokens means words or other knowledge that are used in the dialogue. Let's see how dialogue data is represented in this model. As stated in the previous slide, dialogue, like knowledge, is treated as a triple. All utterances are split into words and then converted into a triple as seen here. So let's take a look at what the Mem2Seq model looks like. As you can see, the memory-to-sequence model consists of an encoder and a decoder. The encoder has the responsibility to encode source input and give the value to the decoder. The decoder decodes the encoded input to generate an output. Now we will look into each of these components in detail. The encoder consists of memories, the trainable embedding layers, and those make up the C1 through C4 in this figure. The query vector Q acts as a reading head over the memories, and it begins with a 0 vector. A soft attention mechanism develops the query vector. It gets the attention P by doing a dot product of the current query and the current top. Then its output is used to make a weighted sum over the next hop. Finally, it updates the query with a residual sum of the current query and the aforementioned output. The decoder loads input sequence of utterances and knowledge into its memories. Instead of using a 0 vector as a query vector, the decoder uses a GRU to generate it. The decoder produces 2 distributions as outputs, the vocabulary and memory pointer. To generate vocabulary distribution, the first hop embedding output and the query vector are concatenated and forwarded to a linear layer. The last hop attention is used as a pointer distribution. Let's take another example to see how the training of the dialogue system works. So this is turn 1. First, the user starts the system and fires silence. Then, the model is taught to respond, "How may I help you?" as a response. The following is for generating a response on turn 2. Statements from the user and the system on turn 1 and the statements from the user on turn 2 are all sent to the encoder in these triple forms. Then, the decoder should create a response that says, "What kind of food would you like?" The training is done so that the system will create this correct response. This is how a response is generated for turn 1. The user's turn 1 utterance is inserted into the encoder as input. The statement is split into the words. In this case, there's only one word. For each word, a triple is generated with information, the information being the word, the speaker, and the turn. The triple is encoded through the encoder, and the result is inputted into the decoder. The decoder then generates "How may I help you?" end of sentence, which is the correct response to this scenario.
Okay, now we will explain we came up with the following two improvements on the system: linear triple summation and positional embedding. We will explain these ideas in detail in the following slides. Our first method changed the way in which embedding triples are combined. For each word in dialog, the 3 corresponding embedding values are extracted from the memory and are added together. Knowledge is also represented as a triple, with similar embeddings in the memory. However, we believe the elements in dialog triple and the element in a knowledge triple may be different. Using a direct sum assumes sufficient training make the memory overcome this. In the original paper, they added up the triple input feature to create a single input feature. Here we call the direct summation. The direct method is the most straightforward approach to combining the triple input feature and has a lower complexity. However, we assume that this method could lose information while doing summation. So we introduced a fully connected layer, which is a trainable component, and replaced with it, as you can see the figure here. We concatenated the triple input feature into a one-dimensional feature and folded into the linear layer. Of course, this can make the model has higher complexity, but we believe this linear method would prevent information loss. Okay, this is our another proposed method of how we represent sequential information in the encoded input. As you can see on this slide, triple input feature only contain a sequence of tone by speakers. In other words, there is no information on when the word was spoken within the tone. Here we assume the word sequence given in a tone is very important to understand its. So we need to include such information. We are using a technique called positional encoding to embed the output from the encoder, as you can see the figure right bottom. Basically, this method injects positional information to the given feature. The frequency depends on the feature dimension, and it uses sine and cosine on even and odd position respectively. This allows our encoded feature representation to have unique sequential information.
Now we will explain our experiment and result. To train our model, we use the following specification. Operating system is Ubuntu. CPU is Intel Xeon. For the GPU, Titan XP was used with 512 KB. With this specification, we trained this model with total 7 iterations, and it took 5 minutes for iteration. In this experiment, we used the following hyperparameters: Adam optimizer with 0.01 learning rate, 3 hops, 256 embedding dimension, 0.2 bar rate on GRU layer. We used a 64 batch size to train. We measured the model performance with all stopping. We evaluated our proposed modification as follows. We used our replication model as a baseline. As the first option, we have Mem2Seq with a linear triple, which denotes a learnable component to reduce the dimension of the triples. For the second option, we have Mem2Seq with positional encoding. Lastly, we applied both options to the Mem2Seq. We evaluated the models on the development set and test set. And for measurement, response accuracy, F1 score, blue score, and dialog accuracy has been used. Okay, first, let's look the results on the development set. The baseline shows the better results on most of the measurements, slightly outperforming the linear triple model. However, Mem2Seq with linear triples shows the highest F1 score. On the test set, Mem2Seq with linear triple show the best performance in all metrics.
We'll discuss the results of our experiments and our findings. We offer error analysis by examining some examples of the system errors. The responses to the same dialog history from each system were collected, and we compare them to see whether our methodology showed improvements. The conversations noted in square brackets refer to knowledge. These examples show that models without positioning encoding were correctly answered, unrelated word candidates were chosen, and these would be sometimes repeated nonsensically. Around 26% of the answers given by the models incorporating position encoding gave repeating word answers. In the case of model that only had position encoding modification, the model failed to give any answer for up to 30% of the questions. In this example, the system recommends a restaurant and the user asks for relevant questions. The user asks for phone number, so the correct answer should be to call knowledge containing the phone number of the same restaurant. In this situation, the models with linear triple modification were able to come up with a better response compared to the baseline, which seems to have failed in understanding the user's intent. The positioner embedding model is again repeating words, while the linear and position embedding model is close but gets the response wrong by omitting the word "the" at the beginning. On the other hand, there were some instances where the baseline answers questions correctly that the linear modification versions could not. So we implemented both our methods for improvement. For our linear triple method, we observed a minor performance boost. The improvement was significant as we hoped. It seems that sufficient training could make direct summation viable. For position encoding, the models with this modification performed poorly. We may have overpowered the original semantic information with position information. We conclude that in the domain of task-oriented dialogue, the user's utterances are relatively straightforward without complicated grammar. Therefore, injecting temporal information may not have been as important as we believed. This was our presentation of our project. Thank you for listening.